Hello everyone, Dr. Matt coming at you from my home studio, bringing you some new videos. Alright, so what we want to talk about today is hypothesis testing for two independent samples. And as you all know, I am a super Arrowverse fan, and so we're going to work today with Oliver Queen is swearing off killing to become a better hero, the paragon he was meant to be. He looked at the penetration of blunt-tipped versus rubber-tipped arrows. And so do these data suggest that the blunt-tipped arrows penetrate further than the rubber-tipped arrows? So I have some data here from 7 arrows that were blunt-tipped and 7 arrows that were rubber-tipped. And so what I did was I wrote a hypothesis that the null hypothesis, the mean between the blunt and the mean between the rubber, the mean difference would be equal to 0. So if we look up here, like that would be reasonable. And then the mean blunt minus the mean rubber is going to be greater than 0. Okay, so the mean difference in penetration between the blunt and the rubber is greater than 0. And so that's because did the blunt tipped arrows penetrate further than the rubber tipped? Okay, so next what we want to do is we want to look for the conditions for inference. Random. I don't know. I mean, it's the same person, it's the same medium, it's the same bow. All right. I'm talking about independent. We don't know. We don't know how he gathered this data. Was it all from one shooting session? Were these different shooting sessions? We don't know. So maybe they're random, maybe they're not. Independent, definitely yes. The performance of the rubber tipped arrows are not going to influence the performance of the blunt tipped arrows. The two arrows are not going to interact, and so independent is definitely yes. There's only 7 arrows fired of each, so 10% of the population, that would be 70 arrows. This is Arrow. He probably fires 70 arrows in an episode, so that's definitely met. And then for sample size, we want to look at the histograms. So I already went ahead and took the data and copied it into Excel. And so for the blunt, Okay, so for the blunt, we can see there's one modal value right here. It's fairly symmetric. For the rubber histogram, you can see it's really kind of spread out. So the blunt one looks pretty good. The rubber one doesn't look great. But what I did was, if you actually went ahead and look at the mean and the mean and the median for the two are very close together. So given that their histograms don't show anything weird going on, we're going to say that that situation is met. Histograms with really small sample sizes tend to be very difficult. It's just one of those things. All right. So now here we go. Now the good part. Provide the calculations. What's the sample mean difference, the standard error, what's the t-stat, and the p-value, right? So let's go ahead and figure those out. As I go back to the data, what I'm going to do is I need to actually transpose this data right here so that it's up and down. And now what I'm going to do is I'm going to take the data. I'm going to go to the data analysis toolpack. I'm going to scroll down to where it has t-test. And we're going to see a t-test with 2 sample assuming unequal variances. It is always okay to assume unequal variances. It is never okay to assume equal variances. Unequal variances will always work even if the variances are equal. Unequal variances will not give you the right thing unless you do have equal variances. So that's really important to know. Now, I've grabbed the data for the rubber tipped and the blunt. I've told it has labels. My alpha is 0.05, and I'm going to output it over here. So right over here. So I go ahead and do that test, and there it is. Now, it gives me a lot of cool things, but it doesn't give me the mean difference. So the mean difference is actually super easy to calculate. Basically, all we're going to do is take this minus this. We're going to subtract the two means from each other. For the standard error, this is also going to be super easy because of the way the table is set up. The variance is actually in the numerator and the observation is in the denominator. and we just need to add the two together. So all four of those values that I need are right there together. And if I didn't have observations that were the same, if these two ends were different, that would be taken care of in here. Now, I do want to point out these variances, different. Okay. Now, when we go to the degree of freedom, usually the easiest thing to do is take each observation, add them together, and subtract 2 because you have 2 samples, so you got to subtract 2. This is conservative, okay? It turns out that if you put this into a degree of freedom calculator, you get something closer to 9.5. This is nice and conservative, and this is a great way of doing it. All right, now, the t-stat is -3. The critical value is 1.8. This p-value is 0.0049. If you did this in your calculator, you probably actually got something like 0.99505, and you would be like, dude, we do not reject. Do not reject. And that would be fine, okay? For this p-value, you would absolutely not reject. But what's happened is this is in the left tail. They've switched this to a left tail, and this would be the less than. See how it's less than right here? And so because it's less than, we would have to subtract from 1. So your p-value here is actually 0.995 blah, blah, blah. Okay? Because you would be looking at all values greater than the -0.31. Okay? So I come over here and we do not reject that the mean difference between them is zeros because we do not have evidence because the p-value is 0.99, what was it? 51. Okay, 51. So this is great. 5-1. And again, why is this? Why did we subtract? That's because remember, Excel always goes from the left, and this was a right tail test, so we had to subtract from 1. Okay, so we're saying that the mean difference is not 1, but we were assuming, right, that the blunt tipped was actually greater than the rubber tipped. But what we actually found out is that the rubber tip actually penetrated more. And so it's possible that there is a difference. It's just that the rubber is different. Okay. So I'm going to go ahead and we're going to calculate our confidence intervals now. Now, what would be the easiest way to calculate the confidence interval is what you need is the t inverse for 2 tails. And you got to have the 2 tails here. Now, the probability is going to be 0.10. It's going to be 10%. And the reason that is because we are looking at 90% confidence interval. Okay, so with the 90% confidence interval, your alpha is 10%. The degree of freedom we are going to use is going to be 12. That is really important. Okay? And again, that's a conservative value. So this right here, this is my, here, let me just move it over. This is my T critical value. So now for my lower confidence interval and my upper confidence level, right? What I'm going to do is I'm going to take the mean difference and I'm going to subtract for the lower, right? The standard error times the T critical. Okay, so all of those 3 numbers are there. For the upper value, I'm going to take that mean difference. I'm going to add to it the standard error times the T critical, and that's going to be my upper value. And of course, -8 is actually bigger than -28. And so that is my actual limit there. Now, I'm just going to round this to 29 and 8. So we are going to have -29 millimeters and -8 millimeters is our confidence interval. And what does this confidence interval mean? We are 90% confidence that the mean, the difference in mean penetration for the arrows, for the rubber, we could put the blunt, right? We could put the blunt. For the blunt tip is between 28 millimeters and 8 millimeters less, because it's negative, less than is between, oh, the rubber. Okay? So, which arrow should he use to stop but not kill? Explain. Um, so obviously here the blunt is penetrating less, so the blunt is less penetrating, right? The blunt is less penetrating, and therefore may be less lethal. Okay, or it's definitely less lethal, or it's probably less lethal, something like that. Okay, so that's that. That's how you do it in Excel. That is how you would calculate the um, hypothesis test and the confidence interval. If you like what I did, please like and subscribe. I'll be putting out content. I'm trying to put out new content once or twice a week, and then putting some of my old content back up on Facebook as people go through the COVID-19. So please like and subscribe, and then comment if this is really helpful for you. Are your teachers using Excel? Are you still stuck with the TI calculator? What tools do you have at home? Comment down below and let me know how you're engaging with your schoolwork while we're on shelter in place.